In this video, we are going to discuss operations on power series. So let f of x be a power series a n x n n goes to 0 to infinity, and g of x be another power series b n x n n goes to 0 to infinity. Then if we are trying to figure out f of kx, we can simply replace the x by kx in our power series and then go from there. We don't need to do a lot of work to find power series for f of kx. For example, if you know the power series for f of x, then you know the power series for f of 5x, f of 3x, f of half of x, f of 0.75x, f of negative 10x. You can just replace the x by whatever kx is, the new x. Same way, if you're trying to figure out power series for x to the power n, we can replace the x by x to the power n in the power series representation and then simplify from there. If we can add or subtract f of x plus minus g of x, same that would be n is equal to 0 to infinity, a of n plus minus b of n x to the power n. We can add or subtract the coefficients in the power series representation. These operations can change the interval of convergence, keep in mind. So if I have two power series here, summation x to the power n is equal to 0 to infinity, and summation x over 2 to the power n, I can go ahead and write them as one expression by pulling out x to the power n and combining the coefficients. So I'll have 1 plus 1 over 2 to the power n in one parentheses times x to the power n goes to 0 to infinity. We know f of x is equal to 1 over 1 minus x, which is summation n is equal to 0 to x to the power n. How do I find the power series for f of 5x? All we have to do is to find the power series for f of 5x, we are going to replace, that would be summation n is equal to 0 to infinity, replace the x by 5x, which can be n is equal to 0 to infinity, 5 to the power n, x to the power n, and that's going to be the power series representation for f of 5x. If I were to find f of x to the third power series representation, I would simply replace the x by x to the third in here, and I would get the power series representation. Summation n is equal to 0 to infinity, x to the third to the power n, which is summation n is equal to 0 to infinity, x to the power 3n. Okay, derivative of a power series. If f of x is equal to summation n equals 0 to infinity a n x minus c to the power n, if this has a radius of convergence r greater than 0, then we can do the term by term differentiation, which is f prime of x would be equal to summation n equals 1 to infinity n a n x minus c to the power n minus 1. So a n is like a constant, is the coefficient that doesn't get changed, but we would reduce the exponent by 1 and exponent comes in the front. So n comes in the front and exponent gets reduced by 1. Now you notice one thing, that we are saying this goes from n is equal to 1 to infinity. We could have left it from n is equal to 0 to infinity. If we left it 0 to infinity, when we plug n as 0, because we have the n sitting over here, my first term will become 0. So that's why we say n equals 1 to infinity. The first term is going to be the 0. When we do the second derivative, we would have n times n minus 1, a n, x minus c, n minus 1. Just a derivative rule applying on x minus c now. Again, this one we are starting from x equals 2 to infinity because my first two terms are going to be 0. When I plug n equals 0 here, I'm going to get a 0 term. When I plug n equals 1, I'm going to get another 0. That's why we're starting at n equals 2. Radius of convergence will stay the same in this case. Whatever was the radius of convergence of original series, that will be the radius of convergence for this new series after differentiation as well. Integration of power series. So if f of x is equal to summation n equals 0 to infinity a n x minus c to the power n has a radius of convergence r greater than 0, we can go ahead and do the integral of f of x dx, which is going to be constant c plus summation n equals 0 to infinity a n. We would add 1 to the exponent here and divide with the new exponent. So add 1 to the exponent and divide with the new exponent. This is term by term differentiation. Radius of convergence r stays the same when we integrate or we differentiate. Find the power series for the following functions. So we're going to find the power series for all these functions. How do we find the power series for 1 over 1 minus x squared? First of all, let's go ahead and realize that 1 over 1 minus x is summation n is equal to 0 to infinity x to the power n. We know that. We also know that what is the derivative ddx? If I go ahead and do the derivative of 1 over 1 minus x, that is going to equal 1 over 1 minus x squared. Derivative of 1 over 1 minus x is 1 over 1 minus x squared. So I can use this to find the power series for this new function. If I go ahead and do derivative on both sides, I would have, let's go ahead and take derivative, 1 minus x equals n is equal to 0 to infinity x to the power n. So derivative of 1 over 1 minus x is 1 minus x squared. That's what we were looking for. And when we do derivative on the right hand side, it's going to be summation n equals 0 to infinity n x to the power n minus 1. So this is a power series for this new function. Now, I also want to find the power series for 2 over 1 minus x to the third power. If you recall, if I go ahead and do the derivative one more time of 1 over 1 minus x squared, it is going to be 2 over 1 minus x squared. 2 over 1 minus x to the third power, because you can do 1 minus x to the second power, negative 2 comes in the front, power gets reduced by 1, and then you multiply with the derivative of inside, which is negative 1, so chain rule. So you do get to 2 over 1 minus x to the third power. So that means if I go ahead and do the derivative of one more time, I would have, so my 2 over 1 minus x to the third can be written as derivative of 1 over 1 minus x squared, and I can go ahead and the derivative of the power series on the right hand side, summation n is equal to, one little change over here. When we do the derivative, it's going to be n equals 1 to infinity, because the first term is going to be 0 when I plug n as 0, so that doesn't need to be written there. N is equal to 1 to infinity. When I do the derivative, n is equal to 1 to infinity, and I have n x to the power n minus 1. So when I do the derivative, it turns out to be n is equal to 2 to infinity, n times n minus 1, x to the power n minus 2. So 2 over 1 minus x to the third would look something like this. It's going to be the power series for 2 over 1 minus x to the third. And then we have the third part, which is h of x. We also want to find the power series for x over 1 minus x squared. So part C is I want to find x over 1 minus x squared. Okay, we already know the power series for 1 over 1 minus x squared. We found it here, so I'm going to use that. The power series for this function is this, so I'm going to go ahead and use summation n equals 1 to infinity. Summation n is equal to 1 to infinity n x n minus 1. So when I multiply this with the x to the power n minus 1 plus 1, that would be n is equal to 1 to infinity, and x to the power n minus 1 plus 1, because there's one exponent here as well. So that would be n is equal to 1 to infinity n x to the power n. And that's going to be my, that would be the power series for x over 1 minus x squared. See another example. Find the power series of tangent inverse x, tangent inverse 3x, x squared, tangent inverse x. So first of all, I'm going to find the power series for part A, which is tangent inverse x. For tangent inverse x, let's go ahead and realize how can I use the geometric series to represent tangent inverse x. So one thing I know, that if I do the integral of 1 over 1 plus x squared dx, that is equal to tangent inverse x. And I do know the power series, actually there's a plus c as well. I do know the power series of 1 over 1 plus x squared. Power series of 1 plus 1 over x squared is 1 over 1 minus negative x squared, which is summation n equals 0 to infinity negative x squared to the power n, which is summation n is equal to 0 to infinity, would have negative 1 to the power n x to the power 2n. Negative 1 to the power n x to the power 2n. So what we can do is, we know the power series representation for 1 over 1 plus x squared. We can go ahead and integrate this. So I'm going to integrate summation n is equal to 0 to infinity negative 1 to the power n x to the power 2n. And on the other side, I do have tangent inverse x. So when I do this integral, I'm just going to switch the sides. That doesn't really make any difference. That is going to give me, that's going to be summation n is equal to 0 to infinity, negative 1 to the power n, x to the power 2n plus 1 over 2n plus 1 plus a c. So that's what tangent inverse x comes out to be. Power series for tangent inverse x comes out to be. But I need to figure out the constant c. To find the constant c, we can go ahead and let x be 0. To find constant c, let x be 0. Actually, look at, you can let x be anything you want, but it would make it more complicated. If I let x be 0, then my entire this term will actually be gone, and it would be easy for me to identify the constant c. Tangent inverse of 0. Make sure your calculator is in radian mode. Tangent inverse of 0 is going to be c, which gives me c is equal to 0. Tangent inverse of 0 is 0. So we can say the power series for tangent inverse x is equal to summation n is equal to 0 to infinity, negative 1 to the power n, x to the power 2n plus 1 over 2n plus 1. That's the power series for tangent inverse x. And we can go ahead and write first few terms when n is 0. Starting with n is 0, it is going to be x over 1, x over 1, and when n is 1, it would be negative, and n is 1, it would be x to the power 2 plus 1 is 3, x to the third power over 3. When n is 0, 1, when n is 2, it would be a positive term, and we would have x to the power 5 over 5 minus x to the power 7 over 7, and so on. So we found the power series for, and it's infinite series. Found the power series for tangent inverse x. How do you find the power series for tangent inverse 3x? Well, all we can do is we can just substitute tangent inverse 3x would be summation n is equal to 0 to infinity, negative 1 to the power n, 3x to the power 2n plus 1 over 2n plus 1. So little bit simplification, I can pull the 3 out and say this is n is equal to 0 to infinity, negative 1 to the power n, 3 to the power 2n plus 1, x to the power 2n plus 1 over 2n plus 1. And that's my power series for tangent inverse 3x. Now we want the power series for x squared tangent inverse x. So that was part B. For part C, x squared tangent inverse x. That would be x squared summation n is equal to 0 to infinity, negative 1 to the power n, x to the power 2n plus 1 over 2n plus 1. So I have x to the second power here and x to the 2n plus 1 here. When I add these powers, I will be left with summation n is equal to 0 to infinity, negative 1 to the power n, x to the power 2n plus 1 plus 2, which will be 2n plus 3 over 2n plus 1. So we found the power series for other functions, which is replacing the argument in the tangent inverse or multiplying tangent inverse x with some powers of x. Okay, another example. Find the power series for natural log of 1 plus x, natural log of 1 plus 3x squared, natural log of 1 plus 3x squared. Again, we need to identify the natural log of x as either as derivative or integral of some function that we know very, very well. We know 1 over 1 plus x is equal to 1 over 1 plus x has a power series summation n is equal to 0 to infinity, negative 1 to the power n, x to the power n. Now, we also know that what is integral of 1 plus 1 over x dx? It's natural log of 1 plus x, right? It's natural log of 1 plus x plus a c, which we can worry about in a minute. So we can go ahead and integrate the power series for this function. We would be able to get the natural log, power series for natural log of 1 plus x. So let's go ahead and integrate power series for n is equal to 0 to infinity, negative 1 to the power n, x to the power n, dx is equal to natural log of 1 plus x. So we can say natural log of 1 plus x is equal to, when we do the integration here, n is equal to 0 to infinity, negative 1 to the power n, x to the power n plus 1 over n plus 1 plus a c. Now to find the value of c, we can choose any value of x, pick something nice. So I'm going to choose x equals 0 to find c. If I choose x equals 0 to find c, let's see what the c come out to be. If x is 0, I have natural log of 1 is equal to everything on the left hand side turns 0 plus a c, which gives me c is equal to 0. Natural log of 1 is 0. So we can say natural log of 1 plus x has the power series summation n is equal to 0 to infinity negative 1 to the power n, x to the power n plus 1 over n plus 1. And that's the power. Oh, I did not need the eraser. N plus 1 here. Yeah. Okay, so once we have the power series for natural log of 1 plus x, we can write power series for any other function. I can write the power series for natural log of 1 plus 3x squared. I'm going to replace the x by 3x squared. Part B, natural log of 1 plus 3x squared would be summation n is equal to 0 to infinity negative 1 to the power n. X gets replaced by 3x squared, n plus 1 over n plus 1. And we can clean up a little bit more, but that would be the power series here. If we want, we can rewrite n is equal to 0 to infinity negative 1 to the power n, 3 to the power n plus 1, x to the power 2n plus 2 over n plus 1. We also wanted to find out the power series for x squared times natural log of 1 plus 3x squared. X squared times natural log of 1 plus 3x squared. That is going to be, now we're going to multiply this power series with x squared, n is equal to 0 to infinity negative 1 to the power n, 3 to the power n plus 1, and I have an x squared now, x to the power 2n plus 2 over n plus 1. And instead of writing x to the x squared times x to the power 2n plus 2, I'm just going to simply change it to x to the power 2n plus 4. I kind of have short space, 2n plus 4, and that would be the power series for x squared natural log of 1 plus 3x squared. All right, let's see, next example. Show that the derivative of e to the power x is e to the power x and integral of e to the power x is e to the power x using the power series. So how can I use power series to show that derivative of e to the power x remains the same and integral of e to the power x remains the same? First of all, the power series for e to the power x is x to the power n over n factorial. It's one of the elementary series, 1 over 0 factorial plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial and so on. X to the fourth over 4 factorial and so on. Okay, so here we have derivative. Now when we do the derivative of left hand side, what does that turn out to be? Derivative of x to the power n over n factorial, which is going to be n over n factorial x to the power n minus 1. This actually, there is a summation sign here that I skipped. Let me go back. There is a summation here. So derivative of summation n is equal to 0 to infinity x to the power n over n factorial. So when I do the derivative, we start n is equal to 1 to infinity because our first term is going to become 0, and x to the power n minus 1 over n factorial. And let's expand the terms for this derivative and see what do they turn out to be. When n is 1, I would have 1, x to the power 0 would be 1, plus when n is 2, I would have 2 times x to the power 2 minus 1 is 1 over 2 factorial. When n is 3, I would have 3 times x to the second power over 3 factorial. Plus n is 4 times x to the third power over 4 factorial. And if you simplify, this is going to turn out to be 1 plus x over 1 factorial plus x squared over 2 factorial, because I would be able to cancel the 3 factorial can be written as 2 factorial times 3, and we can cancel the 3, plus x to the third times 3 factorial and so on. Now let's go ahead and do integration of e to the power x. So I know the power series for e to the power x. Let me rewrite here. E to the power x is summation n is equal to 0 to infinity x to the power n over n factorial. That's the infinite series that we can express using the function e to the power x. So when we do the integral of e to the power x dx, that would be integral of summation x to the power n over n factorial, n is equal to 0 to infinity. That turns out to be n is equal to 0 to infinity x to the power n plus 1 over n factorial times n plus 1 plus a c. Let's choose x to be 0. If if I choose x to be 0, e to the power 0 is 1. So I would have c is equal to 1 here. So now let's see, when I choose c as 1, I would have 1 plus, let's choose n to be 0. X to the power 1 over 0 factorial is 1 and 1 factorial is 1, plus x squared over 2 factorial plus x to the third over 3 factorial, and so on. So you can see that the derivative and integral does not change for the power series of e to the power x. That's another way to show that e to the power x is a stubborn function. It doesn't change no matter what you do to it. You can take its derivative, you can take its integral, it's going to remain the same. Another example, find the power series of natural log of 2 plus 3x. So how do I find the power series of natural log of 2 plus 3x? One thing I do know that 1 over 1 minus x is summation x to the power n is equal to 0 to infinity, right? And this series converges if absolute value of x is less than 1. I also know what is the derivative of natural log of 2 plus 3x. That is going to be 1 over 2 plus 3x times 3, which is 3 over 2 plus 3x. Or I can say integral of 3 over 2 plus 3x, integral of 3 over 2 plus 3x dx is going to be natural log of 2 plus 3x. And plus a c, which we can worry about later. So we see this relationship. Now I'm going to go ahead and find the power series for 3 over 2 plus 3x. We know how to find the power series for this function. I can pull out a 3 halves outside, and it would be 1 plus 3x over 2. Yep. And I'm going to write it slightly differently. 3 halves outside. I would have 1 over 1 minus negative 3x over 2. I'm rewriting the plus sign with the two negatives so I can have the form I need to write a power series, which is going to be, so that's going to be 3 halves summation n is equal to 0 to infinity 3x, and it's going to be negative 3x over 2 to the nth power. Now a little bit cleaning up, I can say this is going to be n is equal to 0 to infinity negative 1 to the power n, 3 to the power n plus 1, x to the power n over 2 to the power n plus 1. So this is a power series for 3 over 2 plus 3x. Now I'm going to go ahead and integrate both sides. So integral on both sides will leave me with the left hand side integral is equal to natural log of 2 plus 3x, natural log of 2 plus 3x. It is going to equal summation n equals 0 to infinity negative 1 to the power n, 3 to the power n plus 1, x to the power n plus 1 over 2n plus 1 times n plus 1 plus a c. Now we do want to find out the c. To find the c, we can let x be 0. Let x equal to 0, we will find out the c here. So we can let x equal 0 to find the c here, and that's going to be, if I let x be 0, 0 to the first power is 0. Yeah, so when I let x be 0, I would be left with natural log of 2 is equal to c. So I get c as natural log of 2 here. Okay, let's see another example. Find the function represented by summation n equals 0 to 2 to the power n x to the power n. So what function did we represent, what function was represented by this power series? We can go ahead and write it in terms of, so let's see, can I say this is summation n is equal to 0 to infinity 2x to the power n, which would be 1 over 1 minus 2x, and that's going to be 1 over 1 minus 2x. This function converges if absolute value of 2x is less than 1. Absolute value of 2x is less than 1, which means I'm going to be between negative half and positive half. It's a geometric series. Geometric series never converges at the endpoints because then your r is equal to 1. Now we have next example. Evaluate summation n equals 1 to infinity n over 2 to the power n as derivative of geometric series. So here I'm given the hint that I'm going to have to use f prime of half when f of x is this function. And I want to get to this function somehow. I'm going to manipulate my function, derivative of my function somehow to get to this point. So if f of x is 1 over 1 minus x, that is equal to x to the power n is equal to 0 to infinity. what's going to be f prime of x? F prime of x would be, f prime of x is going to be summation n is equal to 0 to infinity n x n minus 1. And if I use f prime of half, I'm going to be replacing x by half. N is equal to 0 to infinity n 1/2 to the power n minus 1. I can say this is f prime of half is equal to summation n equals 0 to infinity n over 2 to the power n minus 1. Now in my case, I didn't have 2 to the power n minus 1. I had 1 over 2 to the power n. So how can I get 1 over 2 to the power n? What I can do is I can go ahead and divide both sides with the 2. That would give me, so I can do 1/2 times 1/2. This is going to change my right hand side to n is equal to 0 to infinity n over 2 raised to the power n minus 1 plus 1, because we can add the exponents. It's going to be 2 to the power n. So this is exactly what I need, and that's going to be the sum of this series. Now I know my function f of x was 1 over 1 minus x. What's the derivative of f prime of x? It's going to be 1 over 1 minus x squared. And I want to find the derivative at the point 1/2. So once I find the derivative at point 1/2, I'm going to plug it in here, because that would be the sum of my series. That's going to be the sum of my series. Okay, let's see. F prime of half would be 1 over 1 minus half is 1/2 to the second power, which is going to be 4. 1/2 squared is 4, and it's a complex fraction, so it's going to equal 4. So now I'm going to plug it in there. So I'm going to say, I'm plugging it in here, 1/2 times 4 equals summation n is equal to 0 to infinity n over 2 to the power n. So summation n is equal to 0 to infinity n over 2 to the power n is going to equal to, the sum of this series is going to equal to, it's an infinite series, and it's beautiful that we can find the sum of this infinite series. So we can go ahead and write many terms of this series and see the sum is going to be getting closer and closer to 2. Sum is going to equal to 2 for this series. Okay, another example. We have evaluated the infinite integral. So we want to find the sum of this series using the derivative or integral of a geometric series. The hint would be, because I have starting n equals 2, that kind of tells me that I'm going to have to use the second derivative. Because remember, when we do first derivative, we go n equals 1, second derivative n equals 2. So let me see now. So f of x is equal to 1 over 1 minus x is summation x to the power n is equal to 0 to infinity. What is f prime of x? That would be summation n is equal to 0 to infinity n equals 0 to infinity n x n minus 1. F double prime of x is summation n. Oh, when we do the derivative, this becomes n equals 1 to infinity. N is equal to 2 to infinity n times n minus 1 times x to the power n minus 2. And if I use f double prime of half, let's see, where does that take me? F double prime of half is going to be resembling somewhat n times n minus 1 half to the power n minus 2. Or I can say f double prime of half is summation n is equal to 2 to infinity n minus half 1 over 2 to the power n minus 2. Now I don't want this n minus 2. I want to make it look like the function I have. So I'm going to multiply both sides with 1/4. So I'm going to have to do 1/4 times 1/4, which is same thing as 2 square. It might be better, instead of writing 1/4, it might be better to just call it 2 square. 1 over 2 squared. So 1 over 4 f double prime of half is actually equal to n is equal to 2 to infinity n minus 1 over 2 to the power n, because n minus 2 plus 2 will be just 2 to the power n. Now if I can find this piece, I know the sum of this series. So let's go ahead and look for f double prime of half. We know f of x was 1 over 1 minus x. We just said that in the beginning. And f prime of x is 1 over 1 minus x to the second power. And f double prime of x would be, it would be negative 2 over 1 minus x to the third power, and would multiply with the negative 1. So it's just going to be positive 2. So 2 over. All right, so now we can evaluate the second derivative at any value, 1/2. 2 over 1 minus half to the third power, which is going to be 2 over 1 minus half is half. Half to the third power is 1/8, which is going to be 2 times 8, which is 16. So now I'm going to plug it in here. So this is going to give me 1 over 4 times 16 equals summation n is equal to 2 to infinity n times n minus 1 over 2 to the power n. So that tells me that this sum is going to equal to 4. This sum is going to be 4 for this series. This series, all the terms are going to add up to 4. That's all in this video. In the next video, we're going to look at Taylor and Maclaurin series.